Good morning, students. Today we will study about our next topic, that is electronic configuration, class 11th chemistry, which tells us about the rules of the quantum world. So in last class we have studied about the quantum numbers, that is the position of electron in the structure of atom, and now we will study that how these electrons, they are distributed in different orbitals in the structure of atom. Now here you must know that the architecture of atoms, they shows that understanding how electrons are distributed among the orbital shells and subshells of an atom. So here we will study about the distribution of the electrons in different orbitals, shells, subshells, etc. of an atom. So here you can see we have studied in the last class about the types of subshells. There are four types of subshells we have studied about. That is S subshell, P subshell, D subshell, and F subshell. Now here its full forms that you should also remember. That is S for sharp, P for principal, D for diffuse, and F for fundamental. Now S orbitals, they are spherical in shape. This you have to remember. That is S orbitals, they are spherical in shape and they contain only one orbital. This we have studied in our last class, that is of quantum numbers. We have studied that S subshell have only one orbital and it can hold maximum of 2 electrons. So these are the general things which we must remember for our next considerations or next explanations. Now second, P subshell, this is its full form is principal, and you know that P subshell, that is of dumbbell shape and it contains 3 orbitals which we have studied in quantum numbers topic, and they can hold maximum of 6 electrons, because we know that one orbital can accommodate maximum of 2 electrons. So here we have studied that P subshell that have 3 orbitals total. So it can accommodate maximum of 6 electrons. Now next, D for diffuse, and D have, that is double dumbbell shapes, which are also the complex shapes, and D subshell contain how many orbitals? 5 orbitals. We have studied in last class, that is quantum numbers, and can hold maximum of 10 electrons, because one orbital can accommodate 2 electrons. So 5 orbitals can accommodate maximum of 10 electrons. Now similarly, next F subshell, that is the last subshell we have studied here, that contains 7 orbitals and which can hold maximum of 14 electrons. So these things you have to remember for your next considerations. Next, here you have to remember, that is there are 3 golden rules for writing the electronic configurations of the atoms. But you must know, that is what is the meaning of electronic configurations. Electronic configurations means, what are electronic configurations? Electronic configurations means the arrangement of electrons, arrangement of electrons in different orbitals, right? Arrangement of electrons in different orbitals in the structure of atom, in the structure of atom. Clear? This is the electronic configuration. So for writing the electronic configuration, or we can say for arranging these electrons in different orbitals in any atom, we have to follow 3 golden rules, right? Now what are those 3 golden rules which we have to follow? Number one is Aargaus principle. Number one is Aargaus principle. Number two is Pauli exclusion principle. And number three is Hund's rule of maximum multiplicity. We call it as the Hund's rule of maximum multiplicity. Multiplicity, right? So here these 3 rules are there. which we have to follow for writing the electronic configuration of any atom, or we can say for arranging electrons in different orbitals in the structure of any atom. So these are the names of three golden rules. Now we will explain these rules turn by turn. So here we can first explain Aufbau's principle. What is Aufbau's principle? So here you can see this is a short just term which you have to learn or remember. That is, it is the building up from bottom. From here you can also revise this principle. That is, what is this principle? It shows the building up from bottom, right? Building up bottom means that is from lower thing, you move from lower thing to higher and higher thing. So Abu is this is a German word that is the meaning building up means you will build slowly and slowly higher things. So here what higher things we will do here? This principle dictates the order in which electrons fill the atomic orbitals. Now actually what is Aufbau's principle? It shows the filling of electrons in the increasing order of energies of different orbitals. Here you can see electrons occupy the lowest energy orbitals available first, and then higher energy orbitals are filled after the lower ones are completely occupied. So what is the Aufbau's principle? It shows that the electrons, they are to be filled. What is this principle? This principle shows that electrons are filled in the increasing order of the energies of various orbitals, right? Energies of various orbitals means this principle tells us that electrons will be filled in lower energy orbital first, and then it will be filled in higher energy orbital. Then after that, in the next higher energy orbital, electrons will be filled. For example, first you have to remember this rule also. That is, we will show here from first to seventh period, only S subshell we will write here. Then from second onward, we will write here P subshell. Then third onward, we will write T subshell. This is again according to quantum numbers, because you know that in first shell, there is only S subshell, and in second shell, there is 2S, 2P. The second shell contain S and P subshells. Third shell contain S, P, D. So we will write like this. Fourth shell can have S, P, D, F, all the four type of subshells. Similarly, 5 ka hum likhenge. Then after that, 6 we will write. Then 7 we will write. Okay. Now from here, we will form the order of the atomic orbitals. So first of all, the least energy orbital is first S. So we will write 1s orbital. This is least in energy. Then after that, we will write 2s. Then after that, 2s. After 2s, there will be 2p orbital. After 2p, there will be 3s orbital. Then after 3s, there will be 3p orbital. Then 4s orbital. Then 4s, after 4s, we come to this 3d orbital. Then after 3d, 4p orbital. Then after 4p, 5s comes. So in this way and so on, हम इस तरीके से इसको represent कर सकते हैं. तो least energy orbital is 1s. So this is the increasing order of various orbitals having different values of energies. 1s is lower than 2s, 2s is further lower than 2p, 2p is further lower than 3s. So when we have to fill the electrons, first of all we will fill in 1s orbital. After that, if some more electrons left behind, then we will fill it in 2s orbital. Now, if again some electrons left behind, then that electrons we will fill in 2p orbitals. So in this way, in the increasing order of energies or different orbitals, we can fill the electrons. So electrons are filled in the increasing order of the energies of various orbitals in the structure of atom. This is explained by the Arrhus principle. So this is Arrhus principle, means electrons, they are to be filled in increasing order of the orbitals energy. Now here you must also remember one thing, that is the filling order is determined by n plus L value. Means the electrons filling, or we can say when we compare that which orbital will be lower in energy and which will be higher in energy, that will be determined by the value of n plus L value. From the value of n plus L, we can show that, or we can determine that which orbital will be lower in energy. For example, you have this 1s orbital and you have this 2s orbital, and you have to find that which orbital will be lower in energy. So first of all, see here, what is the value of n here? 1. And what is the value of L here? L, that is the azimuthal quantum number you have studied in previous class. Azimuthal quantum number, that can be, its value can be seen from this S subshell. So for S subshell, we can tell that the value of L is equal to 0. Similarly, here in case of 2s, n value of n is equal to 2 plus L is what? Again, S subshell is here. For S subshell, value of L is equal to 0. So here the total value comes to be 2. Here total value comes to be 1. It means this is the lower value, n plus L value, and its n plus value is more as compared to 1s. So 2s will be higher in energy because its n plus L value is higher as compared to 1s. Clear? So Arrhus principle, that is mostly based on the n plus L value. But here one thing you have to remember, that is if in any case n plus L value is same for two orbitals, n plus L value is same in two orbitals. For example, you can see here in case of 3p subshell, here n is equal to 3, L is equal to 1. Here if we calculate it, it comes to be 4. But in case of 4s, you can see that in case of 4s, the value of n is equal to 4 plus value of L is equal to 0. It again comes to be 4. So here in both cases, n plus L value, that comes to be same. But here you must have to remember that where there is the same value of n plus L value, we must see that the orbital which is having lower n value, the orbital having lower n value, that will be lower in energy, and the other orbital which is having greater n value, that is considered to be, or we can say that will be higher in energy. So these two things we have to remember in Arrhus principle. And Arrhus principle is what? Electrons are to be filled in the various orbitals in the increasing order of their energies. So next, this is the Arrhus principle we have studied. Now next principle, this I have completed, this n plus L rule. Okay. Also remember it, that is n plus L rule. This is also known as Bohr-Bury rule. Bohr-Bury rule, which shows that greater the value of n plus L, higher will be the energy of the orbital. So here this n plus L rule, that helps to determine the orbital energy. The energy of an orbital depends on its quantum number, that is principal quantum number and azimuthal quantum number. Now here you have to remember two rules. Rule number 1, that is, lower the value of n plus L, lower will be the energy of the orbital, and lower energy orbital will be filled first. This is Aho principle, which says that lower energy orbital will be filled first while writing the electronic configurations. And rule 2 is, if two orbitals have same n plus L value, then the one with lower n value will have lower energy, and the other which have higher n value, that will be considered as higher energy. After that, next, our second principle comes, that is Pauli exclusion principle, which we have to follow this rule for writing the electronic configuration. Here it was proposed by Pauli scientist, and this rule ensures that every electron has a unique quantum address, and no two electrons in the same atom can have identical values for all the four quantum numbers, that is N, L, M and S. And from here, just you have to remember one thing, that according to this principle, an orbital can hold maximum of 2 electrons, and they must be of opposite spins, that is spin up and spin down. That may be shown by plus half and minus half. So Pauli exclusion principle explains us, that is, an orbital can have maximum of 2 electrons. So here just you have to remember, that is an orbital. Pauli exclusion principle states that an orbital can have maximum of 2 electrons. Maximum of 2 electrons having opposite spins. Yeah. So this is the second principle, that is Pauli exclusion principle. Now third principle is Hund's rule. We call it as a Hund's rule of maximum multiplicity. Hund's rule of maximum multiplicity. This rule should also be followed by while writing the electronic configuration. What does this rule indicate? This rule shows that if in case of the subshells, like for example, we have p subshell, and we have this, suppose we have 3p3 configuration. We are writing 3p3. 3p3 means p orbital have 3 electrons. Okay, 3 electrons. P subshell have 3 electrons. Now you know that p subshell have 3 orbitals, and 3 orbitals we write in this way. These 3 orbitals we have written, and if the subshell is same, its 3 orbitals will have same energy. So when these 3 electrons to be filled, we have to follow Hund's rule. Hund's rule says that electron pairing will not take place in the orbitals having same energy until each orbital is singly filled. Until each orbital is singly filled means first we have to arrange these 3 electrons like this. First we will write 1 electron here of spin up, second electron here of spin up again, third electron here of spin up again. So this is the accurate way of writing the electronic configuration or arrangement of electrons in different orbitals of the same subshell. Now here we can see that maximum multiplicity when dealing with degenerate orbitals means the orbitals having same energy. Orbitals having same energy. Orbitals with the same energy like px, py, pz. Like I have written here 3 orbitals of this p subshell, and these are designated as px, py, pz orbitals. Now electrons prefer to remain unpaired as long as possible. First we will fill the electrons in the unpaired form, and then only if the more electrons left, then only we will start pairing. So electron pairing in p, d and f orbitals which have more than one orbitals cannot occur until each orbital is singly filled or contains one electron each. So we have to remember, what does Hard's rule of maximum multiplicity shows? It shows that whenever electrons they are to be filled in orbitals of same energy, they should be filled in such a manner that electron pairing should not take place until each orbital is singly filled. Now, why does this happen? Electrons are negatively charged and repel each other, and placing them in separate orbitals means when we arrange them in the unpaired form, that minimizes this electrostatic repulsion and leading to more stability in the electronic configuration. So all singly occupied orbitals will have electrons with parallel spins, and we have to arrange the electrons when we fill them singly. We have to arrange these electrons with the parallel spins. So this is the Hard's rule of maximum multiplicity. And why we call it as maximum multiplicity? Because here, for example, we are writing this configuration. Here, three half spins are there with parallel spins, and here if we calculate the multiplicity value, so this is the plus half, this is again plus half, this is again plus half, so 3 plus half are there, so it becomes equal to 1.5. So here multiplicity value is 1.5. But if we arrange these electrons like this, these three orbitals are there. We arrange two electrons in first orbital and one electron in second orbital. Now here, if we have to calculate multiplicity, you can see that in first orbital, two spins are there. One is showing plus half value, another is showing minus half value. So these two both are cancelling each other, and only second orbital that have plus half value that left behind. So here total multiplicity is plus half. So maximum multiplicity is where? In this type of configuration. So we will prefer this arrangement as compared to this arrangement. So this is the correct way of the writing the electronic configuration, which Hund's rule have explained. So this is the Hund's rule of maximum multiplicity, which shows that electron pairing in orbitals of same energy will not take place until each orbital is singly filled, or until each orbital is filled with the single electron with parallel spins. So this is our third rule. Next, we have completed all the three rules which we will follow to write the electronic configurations. Now there are certain exceptional behaviors in the configurations which we term as anomalous configurations. So what is the meaning of anomalous configurations? That is, there are certain atoms or elements which shows different electronic configurations from that of the expected configurations. So nature prefers stability, and sometimes the standard rules are broken to achieve more stable energy states. So anomalous configuration shows us that due to the attainment of the stability in certain cases, standard rules sometimes they are to be broken down, and in order to attain the stable configurations, we show there the anomalous configurations, that is different configurations. So here we can give the examples of copper and chromium. You can see here, like for example, we have this chromium. Symbol is Cr and its atomic number is 24. Now if we write its configuration, we will write its configuration like this. First we will write the argon, then 4s2, 3d4 configuration. Up to this configuration, its electrons are to be filled in different orbitals. Now this is the expected configuration, but its actual configuration is what? From this 4s2, one electron that jumps to this 3d, and it makes the outermost configuration 4s1 and 3d5. This is the why this configuration is formed here? It is due to the half-filled stability of the configuration. Because in case of chromium, the half-filled configuration is this 4s1 and 3d5. And half-filled configurations and fully filled configurations, always remember that these are the more stable configurations. Now, why these configurations are more stable? It is due to the symmetrical structure and maximum exchange energy. So in case of copper, like you see here, the atomic number is 29. Outermost configuration will be 4s2 3d9. One electron from this orbital jumps to this and it becomes 4s1 3d10, which is the actual configuration. Now here, this 3d10 shows that fully filled configuration. Here in case of chromium, 3d5 shows that half filled configuration. So in both cases, there is half filled and fully filled configuration. And we know that half filled and fully filled configurations are more stable. So these chromium and copper, they will acquire half filled and fully filled configurations in order to attain stability. And now you must also know that why half filled and fully filled configurations are more stable. It is due to two reasons. One reason is that is symmetry, because you know that half filled configurations, like here you can see 3d5. 3d5 means, and you know that d subshell have 5 orbitals. 1, 2, 3, 4, 5. All 5 orbitals have 1 electron each. You can see that if this is the configuration, here in this configuration there is very much high symmetry, and symmetry leads to stability. So this configuration is highly stable configuration as compared to this. So our chromium expected configuration, that immediately changed to this configuration, and the actual configuration of chromium is found to be outermost 4s1 3d5. While in case of copper, again 3d10. 3d10 means there are 5 orbitals. 1, 2, first orbital contain 2 electrons, second 2, third 2, fourth 2, and fifth again 2. So here 10 electrons are there, and this is the fully filled configuration, which is again very much stable. So here these half filled and fully filled configurations are more stable due to two reasons. One is symmetry, because we know that symmetry leads to stability. Greater the value of symmetry, more will be the stability of the configuration. Similarly, second point is exchange energy. More the value of exchange energy, greater the value of exchange energy, more will be the stability. So in case of first case and second case, where the configurations are half filled and fully filled, the amount of exchange energy will be maximum, and there will be maximum stability. So this is the exceptional behavior in the configurations. Now, in the last, you must remember how to write the electronic configurations. We have completed all the rules. We have completed exceptional behavior also. So from all these things, we now try to write the electronic configuration of different atoms. So first of all, for writing the electronic configurations, you will see the atomic number of the atom. For example, I'm taking here the example of sodium. Sodium symbol is Na. We will write its atomic number, that is 11. From the atomic number, determine the total number of electrons. So how many electrons are here? The atomic number that represent the number of electrons. So in sodium, number of electrons are 11. Now, we have to write the electronic configuration. We have to start writing the electronic configuration. How we will write? Number one, we will follow Abo principle. So Abo principle shows that first of all, electrons to be filled in 1s orbital, then in 2s orbital, right? In the increasing order of energies, we will fill the electrons. Now we have total number of 11 electrons, and in 1s subshell. S subshell have only one orbital. You will represent the orbital like in this way, square box type way. You will express the orbital. So this is 1s orbital I have represented. 1 means first shell, S means S subshell. S subshell have one orbital. that is also known as s orbital. Now 1s orbital, this I have made 1s orbital. Now s orbital, because s subshell have only one orbital can have maximum of 2 electrons with opposite spin. I have drawn here 2 electrons with opposite spin. Now out of this 11, I have written 2 electrons here. Now 9 electrons left behind. Now here 2s orbital. 2s orbital again s subshell. S subshell have again one orbital. One orbital can have maximum of 2 electrons. I have filled here 2 electrons. Now after 2s, Arbo principle shows that next orbital comes, that is 2p. Now 2p have 3 orbitals. Here we will write 3 orbitals. Now here 11 out of 11, 4 electrons we have written here, and 7 electrons left behind. So 7 electrons out of 7. Here 3 orbitals are here. 3 orbitals can accommodate maximum of 6 electrons. So we will write here 6 electrons with opposite spins like this. Now 6 electrons we have written. After that, in the last, only 1 electron left behind. That we will fill in the next orbital, who is having more energy than 2p orbital. So it is 3s orbital, and 3s again, s subshell is here. Again only one orbital is present in s subshell, and we can see here only 1 electron left behind. So we will write here 1 electron. Clear? So this is the electronic configuration becomes, and we can show these electrons on this orbitals also, and it will be written like this: 1s2. Similarly, 2s2, it will show that it is having 2 electrons. 2p6, because p is accommodating 6 electrons in total, and 3s1. So the electronic configuration of sodium, that will be written as 1s2, 2s2, 2p6, 3s1. So in this way, we will write the electronic configurations of different atoms. In the same way, you can write the electronic configurations of any of the atoms, like magnesium, whose atomic number is 12, like aluminium, whose atomic number is 13, etc. Any other also. Now here, we have to follow all the rules. First, we have followed Arbo principle. Then Pauli principle also we have followed. Pauli principle shows that an orbital can have maximum of 2 electrons. Then Hund's rule we have followed. Hund's rule here 2p. In case of 2p, we have filled first unpaired electrons in 3 orbitals. Then we have started the pairing of orbitals, pairing of electrons in different orbitals. So this is the way to write the electronic configurations.